So good morning students. Today we will talk about elements of greedy strategy. So in our last lecture we have talked about greedy algorithm and the basic principle behind this strategy, and we have also discussed a little bit the difference between dynamic programming and greedy algorithm. One particular problem like activity selection problem, that also we have discussed. So during the discussion of activity selection problem, what we have seen that a problem which we want to solve using greedy algorithm or greedy strategy, that must show optimal substructure and one another property that is called best choice property. We can solve one problem using greedy algorithm. So activity selection problem is such kind of problem where you have seen that that problem is having optimal substructure property along with the greedy property, that is best choice property. So today we'll elaborately discuss elements of greedy strategy. That means the same thing what just I said. Uh, a problem which we want to solve using greedy algorithm. How can we decide that whether that problem can be solved using greedy algorithm or not? Okay, so that's why we need to learn the elements of greedy strategy. And other thing is that how would we proceed to solve a problem using greedy algorithm? What are the different steps? Like in dynamic programming, we have seen that there are 4 steps to solve an optimization problem using dynamic programming. The first one is to characterizing a structure of an optimal solution, then find a solution, optimal solution using recursive formula, okay, and getting the optimal solution by solving the recursive formula, and then finally we construct an optimal solution. So these are the 4 steps of dynamic programming. Similarly, for greedy strategy, we have certain steps, so we'll be talking about that also. So as we know that greedy algorithms also find optimal solution, or we apply on optimization problem. So it gives optimal solution to a problem, but it is not always possible to get optimal solution using greedy algorithm. So we will see some example that for few cases or some cases greedy algorithms can give optimal solution, but in few cases it may fail. So we'll talk about that also. So finally, greedy algorithm on the problems we will be applying, they will be able to solve greedy optimal solution like activity selection problem we have talked about. So two main elements, as I said, that one is best choice property or the greedy choice property. The best choice property is defined like in the way that a particular solution to a problem will be considered that is best at that moment. Okay, it will not look into the other sub-problems by solving them individually, and then it will decide that which particular problem solution is optimal. Instead of that, at the moment, the solution which looks best, that will be selected as a greedy choice or best choice. Best choice. Okay, and this idea is called greedy choice property. And another thing that I told, that is optimal substructure. So if we remember the activity selection problem, so in activity selection problem we have seen that a subproblem is defined in this way, Sij, okay, where Sij denotes all the activities within the range of the finish time of AI, that is Fi, and start time of Aj, that is Sj. So all these activities within this range will be included in this thing. So we want to find out optimal solution, that is for activity selection we want to find out the maximum subset of the activities or maximum of the compatible activities, actually compatible activities or exclusive compatible activities. Okay, uh, their span does not actually overlap, so that they can be they can use the resource at their own time. Okay, so there will no overlap. So in this way we represent one sub problem in activity selection problem. Okay, and if we want to find out solution, optimal solution for this one, then we need to find out optimal solution for some smaller sub problems within this range. Suppose some optimal solution we have k, which is a sub problem, and within this problem Sij. So that is called optimal substitute property, and the basic definition of optimal substitute property, that an optimal solution contains optimal solutions to the sub problems. So that we have seen in activity selection problem. So these are the steps actually we need to follow to develop a greedy algorithm for a problem, or a problem which we want to solve using greedy algorithm. We need to follow these steps. First, we need to determine the optimal structure of the problem. It is similar to the dynamic programming. The characterization of the optimal substructure of an optimal solution, and then develop a recursive solution. It is also similar to the dynamic programming, a problem which we want to solve using dynamic programming. So we use the same recursive representation, and we need to show that a greedy choice will keep one sub problem after this. Like if we remember the activity selection problem, even the sub problem we were talking about Sij, but finally we came to one sub problem, that is Sk, where we have one index k. What it means that all the activities after the finish time of Ak, that is Fk. Okay, so it will include all the sub problems, all the activities after whose start time after Fk, or finish time of Fk. So if we have the entire sub problem S0, okay, so this is the entire sub problem, then if we choose the best one, like suppose A1 is the best one because A1 has the least finish time among all of the activities, then we will take out this as the best choice at the current moment. Okay, and this we can do because all the activities are sorted monotonically increasing order by their finish time. So we can know that A1 is the least, the activity having the least finish time. So we'll be taking this one out from S0. So finally we'll have a one solution sub problem remain, that is S1. Okay, so that means one greedy choice will remain one sub problem instead of more than one sub problems, what we have seen for dynamic programming. And after that, we have to prove that the shape with the choice actually is safe. It will not actually violate any other the properties of the greedy strategy. And then finally, we will develop the recursive algorithm using the recursive formula or expression we have developed before, and we can develop a recursive algorithm for that. Okay, and then finally that recursive algorithm is converted into an iterative algorithm. That also you have seen in activity selection problem. Now the first one, first element we are talking about, that is a greedy choice property. So greedy choice property is that it gives you an optimal solution, or optimal solution can be obtained by taking a sequence of locally optimal solution or locally optimal choice. Okay, that means at each instant or each moment or each stage, we will take the best out of all the options. Okay, and then that will be included, or the result of the solution to the sub problem will be included with all the previously best selection, and finally we'll be getting an globally optimal solution. So hoping that we will be achieving global solution, global optimal solutions for the problem. A local optimal solution is obtained by choosing the best option at the moment. So another thing is that in greedy choice property, dynamic problem we solve all the problem and then we choose the best one. But in greedy choice property, we don't need to see the other sub problems. Only it will depend on the previously selected best choices or greedy choices. Then we will select the best one at the current moment or at the current stage, and then there will be no overburden or burden of calculating or solving all other sub problems to find the best one, what we do in dynamic programming. Okay, so if you see the activity selection problem, the first problem is S0, then we take out A1 from the problem and the sub problem we remains, that is S1. Then we take A2, suppose, which is the list finish time, then will remain S2 as the sub problem. So if we draw this kind of graph or tree for the dynamic programming, greedy strategy for activity selection problem, so we use a top-down procedure. But in dynamic problem, what we do, we start solving the smallest problem or smaller problem before solving the larger problem. So initially at the leaf level, we solve the problem and then we use these optimal solution to get optimal solution for one level above or large problem. So here in dynamic programming, we use bottom up, okay, or we can use the memoization top down approach. But even in memoization top down approach, we solve the sub problem, smaller problem first, and then we can obtain a solution to the bigger problems. So this is the difference. And greedy choice property, as I said, that it will give optimal solution, globally optimal solution by choosing locally optimal solution. Another element that we talked about, that is optimal substructure. So optimal substructure that also be exhibited by the problem. Then we can attempt to solve that problem using greedy approach. If finally we see that we have the greedy choice property valid for the problem. And one more thing that you need to understand, that when we will apply greedy algorithm or greedy strategy, we will take the best option, but that will leave one sub problem instead of more than one sub problems. So if it happens for one particular problem, if we can map the problem or solve the problem in such a way that we can find an optimal substructure property, and then at each stage we choose best choice, and then it leaves one sub problem, then we can say that this problem can be solved using dynamic greedy algorithm. So in dynamic programming, we have seen it is little bit complex, or you can say little bit heavier than greedy strategy, because in dynamic programming, before choosing one particular the best option, we need to solve all possible options and then we choose the best one. But in dynamic programming, greedy algorithm, we don't need to solve all the sub problems. Only we look into the sub problem and choose the best one. Okay, then we can use greedy strategy or greedy algorithm. So that is possible in some cases, that is not possible for all the cases. That's why greedy strategy does not give optimal solution for all optimization problem. Now there's a difference between greedy and dynamic. Already I told you this thing, that greedy and dynamic difference between that. Both the problem, if we compare them, both the problem or both the approaches show that optimal substructure. Okay, but one thing, that in dynamic programming, all the sub problems should be solved before choosing the best one. But in dynamic greedy algorithm, we need to apply the best choice approach, where we don't need to solve all the problems before selection. And other thing is that greedy algorithm uses top-down approach, where dynamic programming uses bottom-up approach. Okay, And one like the confusion may arise because you see the elements or the steps we discussed just now, that in dynamic programming the four steps we apply, and they based on actually the optimal substructure along with that overlapping subproblem. And greedy algorithm also looks like optimal substructure. Okay, so maybe like in confusion may arise that sometime we are trying to solve the problem using greedy strategy, but actually it cannot be. Okay, it can be solved using dynamic programming only, or sometime it may happen vice versa, like the problem which can be solved, we are trying to solve in dynamic programming, but greedy strategy is more better in terms of time efficiency and all. So that thing we need to understand the intuition, and the experience will tell you that which particular algorithm we should use to solve an optimization problem. Okay, so that also we'll talk about. So here this knapsack problem will give us one clear picture that how people can be confused in applying dynamic programming or greedy strategy for solving one problem. So there is a very common or popular name that is called knapsack problem. There are two versions of knapsack problem. One is a 0-1 knapsack problem, and another is a fractional knapsack problem. The idea is very simple, that it is a story kind of thing, like a thief is trying to rob one store, okay, where he is having a knapsack of capacity W pound, okay, and there are n items in the store, and each item is of worth I dollar, suppose, and the weight of each item is WI pounds. So what do you want to he wants to do, like he wants to take maximum profit by taking specific items instead of taking randomly. He wants to rob the maximum items of maximum worth. Okay, so this is the but in 0-1 knapsack problem, one thing is that one item can be taken entirely or the completely, not the fraction part of it. Okay, so it is kind of binary whether he will take the item or he will not take the item. Okay, so based on that, it is named as 0-1 knapsack problem. Another is fractional knapsack problem. The idea is same. The only thing is that thief can take fraction of any item. So the objective is to say same in both the cases, that the thief wants to take the maximum item of maximum worth, okay, or maximum value. So both the problem you can see exhibits optimal substructure property. Why I am saying that? Suppose there are n items, okay, n items. So the thief will take one item at a time, selecting one item. So we'll be living with n minus one item. Okay, and then after taking second item, it will be living with n minus 2 item. So if we want to find out optimal solution, suppose we denote the optimal solution, suppose an, so it will contain one item that we have taken, that is suppose a1 or w1 or whatever. So then it will be the union of an minus 1. So optimal solution A n depends on one item what you have taken at the time, and the optimal solution for n minus 1 item. So this thing knapsack problem shows optimal substructure property for 0-1 knapsack problem or fractional knapsack. So both the problems show actually optimal substructure property. But here we see that even the fractional knapsack problem can be solved using greedy strategy, but 0-1 knapsack problem will not give optimal solution if we are using greedy strategy. So that we can explain with an example. Suppose we have three items, item 1, 2 and 3, where weight of the three items 10, 20, 30, and the value for each item is $60, $100, and $120. and the capacity of the knapsack is 50. So the idea is that we just find value per item. Okay, value per item or value per unit weight actually. So this case, for this item we will be getting 6 value per item. This will get 5 and this will get 4. So based on this value per item actually, or a dollar per item, you can say dollar per pound. So we will take that item which is having the maximum dollar per pound. Okay, because that will give you the maximum benefit or maximum profit. Okay, to the thief. So here he will take this item entirely. So we can think like that. First we are taking fractional knapsack. Okay, so we will take this thing because this is giving the maximum dollar per item or dollar per pound. So we will take this entire part 10 here, and then we are having these two items. So this is giving maximum dollar per pound 5. So this will also be taken entirely 20, but we are left with this part only, that can hold only 20 because 30 capacity of the knapsack is complete or full. Now only the part of this item can be taken out, that is 30 20 out of 30. So the total amount of the what the thief will gain out of it, that is dollar 240. Okay, dollar 240. So in this way we can see that knapsack problem is giving you this optimal solution for if you using greedy strategy. But if we use the greedy strategy for 0 1 knapsack problem, what we'll get the similar way, either we can take a complete item or we cannot take the item. So if the first item is giving the maximum dollar per pound 6, so we'll be taking this entirely, this one 10. Okay, then the next item we are having, that is item 2, which is giving the maximum dollar per pound. So we will be taking this entire thing, but we need to see whether that 20 capacity is available in the knapsack or not. Yes, it is available. So sorry, we are taking this one. So 20 we will be taking. So here we are left with 20 only. So sorry. So in 20, this empty capacity, we cannot take this last item we are having here. So only the total optimal solution we are getting, that is 160, but this is not the optimal one. Okay. And other case, if we see that we can take 5 and 4, so 5 and 4 means this one person, so we are getting only 180. Okay. But if we take 20 first and then 30, this one completely, sorry, here we have taken 6, means 10 item 1 and then this. So but if we take this item 2 completely first and then item 3 completely, here the knapsack is full and the optimal solution we are getting $220. Okay, so in this case what we can say, that for a 0 1 knapsack problem we cannot apply dynamic programming like a greedy algorithm. If we apply the greedy algorithm, so it will not give you optimal solution. Okay, but in fractional knapsack problem, it is giving, or it is able to give you optimal solution. So from this idea, what you can see, that greedy algorithm cannot be used always for giving optimal solution. Now, one particular problem, or you can say the coding problem, okay, which is called Huffman coding. So in Huffman coding, the greedy strategy has been used to code the characters present in a text or in a file. Okay, the idea is very simple, that we want to encode the text or characters in a file in such a way that the total number of bits required, that will be minimum. So that is, this is also an optimization problem. So we want to optimize the number of bits needed to encode or represent the characters or the entire file. So the Huffman codes is such a coding style strategy where the greedy paradigm has been used to encode the characters. So it is observed that if we apply Huffman code to compress a data, so it saves actually 20 to 90% of the memory. Okay, like number of bits we need to spend lesser than other techniques. So suppose we are having a file consisting of 1 lakh characters, okay, and the file is containing the text which are composed of 6 different characters A to F. Okay, so there are mainly two approaches. One is called the fixed length code word and another is variable length code word. Code word means that binary representation of each character. Okay, so fixed length code word means if we have 6 different characters, so we can use log this one 6. So this will give you 3 bits at least. So for each character we need to use 3 bits to encode different characters. Okay, and suppose the binary strings we are using to represent these characters A 000, B 001 and in this increasing order. Okay, so the total number of bits we need to encode this or represent these 6 characters in a file containing 1 lakh characters, total characters. So total number of bits we need 3 lakh. Okay, because 3 times bits are required for each particular. Can we do better, like if we have any other option so that the number of bits we can use to encode the entire file that is lesser than these 3 lakh bits. So variable length code word we can use. So suppose we have used like idea where what it says that uh, a character which is very frequent or which appears many times in the text, so that is represented by smaller number of bits, and the characters which is infrequent actually, that can be represented in some larger number of bits. So obviously when a frequent word is represented by smaller number or very small number of bits, then obviously the number of bits we need to represent the entire encode the entire file will be lesser. So here we see, suppose for different characters, suppose A is represented by 1 bit, B is represented by 3 bits, C is represented by 3 bit, D is represented by 3 bit, E is represented by 4 bit, and F is also represented by 4 bits. Suppose, okay, so the total number of bits and their presence here reported here that A is present 45 times. Okay, 45 times, that means 45,000. Okay, 45,000 times. Okay, so in thousand. Okay, then 13,000 or 13, 12, 16. So we can calculate the total number of bits we need to use for representing or encoding this entire file. So that is 224,000 bits. That is at almost 76,000 lesser number of bits. So it saves 25% of memory approximately. So variable length code word actually saves the memory. So Huffman coding is actually based on this idea, variable length code word. So as I said that Huffman code uses variable length code to compress file. So here the idea is that zero actually is used to represent the most frequently occurring letter or character in the file. Okay, so which saves many number of bits. Okay, so it is actually Huffman coding is a kind of prefix code. So prefix code is what? Prefix code, that a code which is not present as a prefix in any of other code. Okay, so prefix code defines the code in which no code word is also prefix of some other code word. Okay, like suppose we have 0 as the first code word for any character, then one one code word will never start with 0. Okay, will never start with 0. Like it cannot be a code word like this one, because otherwise this 0 actually is a prefix of this string. So that will be an ambiguous situation. So we cannot decrypt or decompress the file after compression. So that's why it is based on the prefix coding. So the same example we have taken, suppose this variable length we have already talked about, that fixed length we take in this way and the variable length. So the bit we save number of bits, that is 76,000. One main important thing is that how encoding actually we do, because if it is not prefix code, so there will be a problem, because we won't understand that which is a valid code word in the compressed file. Okay, so that's why prefix code is an idea. So, but in prefix code, one advantage is that we can easily identify the initial code word of in the text or in the compressed file. So, if we identify the initial code word, then next code word also be identified easily, because no code word is a prefix of any other code word. So, suppose we have a string of this kind. We have a string of this kind. Okay, 0 1 0 1 1 0 0, where it is denoting A, B, C, where A is a code word for A is this, code word for B is this, and code word for C is this. Okay, so you see, if when we'll decrypt or decompress this one, we just read the first this one, and it will match with the uh, any of the code word like 0. So no code word except A is starting with 0. So obviously this first one will be represented as A. Then it is leaving this thing. So we will begin with 0. So it will take the first character. Now we are living with this one. So we will start counting 1. So 1 actually, 1 is starting for B and C both. So we will go for the next bit to check which actually we are looking for. So 0. So 0, in both the cases we have 0. Okay. And then finally we have 1. So here we have 0. So after 2, 0, 1 we are having 1 actually. 1 actually. So this will be identified as B, this part, and then we are left with 1. So it again starts with 1. This also 1 starts with 1. So there is a confusion. So we will go for the next one. So again, next one is also having same like in B and C both. So the last character will say that this is actually C. So in this way, this prefix code will help us to understand that which is the initial code word, and as these are prefix code, so there will be no code as a substring or the prefix of any other code. So we can easily understand, or we can easily interpret that which code word is being represented by this one. Okay, so this is the advantage of prefix code, and this idea along with that the frequent characters and infrequent characters, they are represented by a variable number of bits. So the frequent word is represented by smaller number of bits, and infrequent words are greater number of larger number of bits. So that is an advantage. So in this way, it actually avoids the ambiguity also in encoding and decoding. So actually this is happen by using a tree-like structure. You can say that Huffman tree, or you can say a binary tree. Okay. So if we use a very fixed length code word, so this binary tree is denoting what? That each leaf is denoting a character. Okay. Leaves are the characters, and internal nodes are denoting the occurrence of these characters. Okay. So the one child of any node denotes that if we are having 0, so we will go to the left child. If it is 1, then we will go for right child. Okay, so this is for decryption. Okay, or also encryption. We know that if we want to find out that which particular code word we need to use for encrypting, so we just go from root to leaf, that which where it is actually as a leaf. So we can go to root to that leaf node, and we can read all the symbols 0 1 present in the path. Okay, so in this way you can use. One thing you can see that in fixed length representation, the tree is not a full tree. Okay, the tree is not full tree. But if we take the optimal prefix code or Huffman code, so it's a full tree. That means each node is having two children. Okay, so this is the idea tree representation. So actually, Huffman code generates a full binary tree for the characters present in different numbers in the text file. Okay, and then we encode these characters uh, based on uh, based on this tree structure. Okay, so how would you encode the characters? That is the main thing. That how do you get an optimal binary tree or full binary tree for the characters present in a text? Okay, so the simple thing is that it is based on the grid strategy that for each character representation we choose the best one. Here the best one represent the maximum number of occurrence or appearance of one character in a string. The character which appears in largest value or largest number, that is denoted by a smaller value, that is denoted by smaller number of bits. Okay, and then the next one also will be denoted by some larger number of bits, and this way gradually the very infrequent word or character is represented by the largest code word. Okay, so we can see that it is an optimal prefix construct and optimal substructure property also here it is having. Like if we want to create an optimal code word for the different characters, then we start with the code word, okay, for the frequent maximum frequent word. So the tree structure, we can have this representation for grid. So we have suppose C set of n characters. Okay, so each character has have certain frequency of occurrence that is denoted by FC. Okay, and we have n leaves for n characters and n minus 1 merging operations we apply here. So n minus 1 nodes, internal nodes we have also here. So we use a maximum priority queue, minimum priority queue to find out the minimum value, okay, minimum presence of any character. Because here we'll see the tree is constructed from leaf node to the root node. Okay, so we will take that node as the first leaf which is having the least occurrence in the tree. Because when you come from root to leaf, so the first leaf which we are considering or we are creating in the tree, that will be the furthest leaf from the root to that node. So that in that sense, it will have a longest code word in the tree or in the compression procedure. So that will give you longest one. So first we will consider those characters which are appearing or the frequency of these characters are very less. So what we do, the algorithm is very simple in this way that Huffman code takes C as set of characters, okay, along with their frequencies given. So n is denote number of characters denoting. Okay, Q is a priority queue where we are inserting all the frequencies, actually frequencies of all the characters in the priority queue, and starting from 1 to n minus 1. So here suppose we have C, okay, C character or C characters here. So which character we will be checking? Suppose we want to find an optimal solution for C. Okay, suppose that is Cn. So we will be taking the best one, that is suppose Cx. This is the best one at the time. Then we will find out the optimal solution for Cn minus 1. So it will give you that optimal substructure property. Okay, that optimal solution for Cn can be obtained by optimal solution to the subproblem Cn minus 1. Okay, so we will traverse all the nodes of the priority queue one by one. So allocate a new node Z. So it is one node we are creating for the tree. So the left subtree of the tree will be the extract minimum. That is when the minimum occurrence of So X will take minimum uh, the character which is having minimum occurrence, and then the next character which is having the second minimum occurrence, and then both are frequency are we are taking the sum, and then we create one node, okay, root node for this subtrees and insert in the tree, and we do this thing for all the characters present. So this example will show you this how it is done. So initially all the nodes are pushed into a priority queue, okay, and their frequencies are also reported here. 5F is 5 times present, E 9 times, C 12 times, the thousands we are denoting by normalizing it. But B is 13 times, D is 16 times, and A 45 times. So how this algorithm is doing? It is taking out the smallest, the character with smallest presence. So that is F5 that we know that using minimum priority queue we can do it easily. And then the next one, this one, and both these two things. This first one is create the left node, and the second was create the right node, and the corresponding branches are labeled with 0 and 1, and then we get the sum of the two values 5 and 9, so we are getting 14. Okay, then we this is inserted into the priority queue again, so again the elements are sorted in this way. Okay, even here you can see that these are at the initial position of the priority queue, but after inserting this one, it will reshuffled and we get this order of the characters. Then we take two smallest characters, or number of characters, less number of frequency. Then we take the sum of this. So we get this one, C as a left node, right node, and then we get this structure, and we again reshuffle them to sort them. And then here the smallest value is this one, this one. So this will become the left subtree, okay, and this will become the right subtree, so this one, and then we get the sum 14 and 16, that is 30, and labeled with 0 and 1, and then again 25 and 30, we merge them and we get this subtree, and then this 45 and this subtree, and finally we are getting this complete full binary tree for getting the different codes for the different character. So actually we get an optimal solution or the code word for uh, encoding the different characters present in a text. Okay, so the number of characters we need to, number of bits we need to represent or encode the entire file is required less. Okay, and the time complexity we're talking about, that we need to construct a mean heap. So mean heap, we know the build mean heap takes order of n times. Okay, order of n times, and we extract the mean and insert the queue operations n times. If you see the algorithm, so actually actually the time complexity becomes n log n, because we have seen in the algorithm that we run the loop for n times, and every time we extract the mean priority queue. Okay, so the accessing that one we need n log n time. So actually the machine is not responding. Okay, so there's a problem in the PPT. So actually, the time complexity we can calculate, that is n log n. Okay, for Huffman coding. So in this lecture, we discussed the different elements of greedy algorithm. Okay, so we have learned that greedy algorithm to solve the problem, we need to see that whether it is exhibiting optimal substructure property and best choice property or greedy choice property. Then you can apply greedy algorithm for that instead of applying dynamic programming. So thank you for today.